Okay, so last class, this is the last thing we looked at, right? Calculating average atomic mass, and we did one practice exercise also. So once again, calculating the average atomic mass, we need mass contribution from each isotope. And how do we calculate mass contribution from each isotope? The abundance given in percentages, multiply that by the atomic mass given, and then add up each of the atomic masses together to get the average atomic mass. We did practice exercise 2.4. That was the last problem we did in last class. That is silicon's 3 isotopes, and we have calculated the average atomic mass. Do you want to do one more problem of the same kind? So that just to remember that. So I'm going to give you a problem from the end of chapter itself so that you can all read from your book and do the problem. So let's go to page number 71. And let's do question number 35, 2.35. Naturally occurring magnesium has for the following abundances. So you have 3 isotopes of magnesium, magnesium 24, 25, and 26. Abundance is given in percentages, and atomic mass is given in atomic mass units or AMUs. Now there are 2 questions. What is the average atomic mass of Mg, and sketch the mass spectrum. Let's forget about the sketching mass spectrum part. I don't want you guys to sketch the mass spectrum or anything, but let's calculate the average atomic mass. Okay? So again, to calculate the average atomic mass, let me get my pen so that I can work with you guys. So this is not 2.44, but we are going to do 2.35 from the exercises. So 3 isotopes. First one is magnesium 24. So if you calculate the contribution from magnesium 24, we need to multiply the abundance with the atomic mass. Now abundance is given in percentages. What do we do with percentages? Convert that to decimals. So we will get 0.7899, 0.7899. Multiply that by atomic mass 23.98504. 23.98504. Do the math, please. Then the next isotope, Mg25, abundance is 10%, 10.00. How do we use that? 0.1000. Multiply that by its atomic mass is 24.98584. So 24.98584. Again, you can finish the math. Abundance for the next one, 11.01. So that becomes 0.1101. Multiply that by its atomic mass, 25.98259. 98259. Okay, now can someone give me the numbers you get here? 18.95 corrected to 4 sig figs. Good. Second one, please. 3 point or 2 point? Okay. 2.499 And the third one? 2.8607. So it will become 861. So these are the individual mass contributions, and the average atomic mass is, what do you do once we get these numbers? Just add all of them up. So let's add all of them up. What do we get? 24.31. Unit is AMU, because all the atomic mass is given in AMUs. So that's the unit you know right now. Later we might learn a different unit for atomic mass. So magnesium, where is that in the periodic table? Let us check what they give. Well, that periodic table, I can't even see the letters. Yep, in your periodic table, they haven't corrected it for 4 sig figs, 24.3050. So your answer is correct. 24.31 is the answer. So this is how you calculate the average atomic mass, okay? So this abundance and atomic weight will be given to you. All you need to do is multiply for each of them and then add up the numbers. So now we are going to look into the periodic table, a little bit details on periodic table, that is how do we classify periodic table, what are those columns, what are those rows, what are they called, how these elements are arranged in the periodic table. So we are going to look at those things. So the periodic table is a systematic catalog of elements. It's not that, just whatever symbol you could find, you just put them on. There is a system, or there is a particular order of arrangement. The first thing we are going to notice is elements are arranged in the increasing order of their atomic number. So the first element, hydrogen, has atomic number 1, then comes helium, then comes lithium 3, then comes beryllium 4, 5 boron, so on. So the elements are arranged in their order of atomic number. Atomic number is also the same as, what is it? We learned that in last class. Number of protons in an atom. Now we see the columns and rows on the periodic table. We don't call columns and rows anymore. We are going to have names for it. So the rows on the periodic table are called periods. So if you look at the periodic table, you will see that there are 7 periods. The rows you see on the periodic table. Okay? So there are 7 periods. We would just call it first period, second period, third period, so on. And then we have columns in the periodic table, and the columns are called groups. Again, if you count the total number of groups, you should find 18 of them. There are 2 different ways of labeling them. That periodic table is not a good one. If you look into the periodic table on the, your book, first page, inside cover, everyone got the periodic table? Okay. If you see above each group, that is each column, you would see 2 different types of numbering, right? There is the the Arabic numeral 1, 2, 3, 4, 5, 6, so on, all the way to the last one, that is 18. So there are total 18 groups. And then you have 1A, 2A, and then in the middle you 3B, 4B, so on. And again to the right side you will see 3A, 4A, 5A. That number with a letter also. So that number with the letter, that is the US method of labeling the groups. Okay? The number with a letter, the A letters or B letters. And the IUPAC, or International Union for Pure and Applied Chemistry, who is the worldwide authority in naming anything, or who has the last word in everything about chemistry, they label just group 1, 2, 3, so on up to group 18. However, we will be focusing on that US method of labeling, that is A groups and B groups. Okay? Now, so those columns with the letters A along with it, that is 1A, 2A, and then 3A, 4A, 5A, up to 8A, those groups are called main group or main group representative elements. Those are the elements you will be working with most of the time, the main group elements. And then in between what you have, those B lettered groups, they are called transition metals. And then we have two periods like given at the bottom of the periodic table. They are actually not a separate two periods, they are part of period 6 and period 7. If you look in the periodic table of your book, you can see that in period 6, first two elements, number 55 and 56, after that there is a gap, right? Again in the 7th period also, after 87 and 88, there is a gap. And if you look in the book, that gap is expanded and given in the bottom. So that what you see in the bottom, they should actually fit into that gap. Just to make the periodic table kind of look concise, it's just given in the bottom. We will again learn in more detail why they are there and what is the speciality. Yes?
Do they have groups, the ones that are at the bottom, since they're kind of
We would, no. That's what I said. Later we will learn about these two periods which is given in the bottom more in detail. Right now we will be focusing only on the main groups. Okay, we are starting with main groups, and slowly you will increase your understanding of the periodic table. So, elements in the same group have same or similar chemical properties also. Right now, say for example, helium number 2 is a non-reactive gas, or it is one of the group 8A element, the noble gas, and the element comes after a noble gas is a soft reactive metal. You can see this pattern repeating all through the periodic table. Every noble gas, helium, then comes neon, then comes argon. If you look at the last group in the periodic table, helium, neon, argon, krypton, xenon, radon, it goes like that, right? So if you look at those gases, they are mostly, all of them are gases and they are non-reactive. And if you just look at the elements coming just after them, they are always a metal, very reactive, and a soft metal. So we can see, this is just an example of one trend. There are a lot of periodic trends which we will learn slowly as we go further, okay? This is just to say, kind of an example giving you that when we look at the periodic table, we can figure out a lot of trends. Now, these 5 groups in the periodic table are usually known by these common names rather than 1A, 2A, 3A and all. Group 1A is usually known as alkali metals, and the elements are lithium, sodium, potassium, rubidium, cesium, francium. You can see those symbols are in the first group in the periodic table, right? When you start from hydrogen, even though it's given usually in the periodic table above the first group, please note that hydrogen is not a first group metal, okay? It is not part of first group. That is why in the periodic table hydrogen is given above the first group, but not that it is not joined to the first group, okay? So there is this gap in between, so don't think that hydrogen is the first group element. Now group 2A is usually known as alkaline earth metals. Again, beryllium onwards, beryllium, magnesium, calcium, strontium, barium, radium. Then group 6A are called chalcogens, and that is the oxygen family, oxygen, sulfur, selenium, tellurium, polonium. Then group 7A are halogens. Halogens are one group which we usually see very often, fluorine, chlorine, bromine, iodine and astatine. And group 8A, as I said, that is the noble gases or rare gases, helium, neon, krypton, argon, krypton, xenon and radon. So these 5 groups, they have these common names, and usually in the book you might see the group name or the common name. So you should be aware of their common names. Now, so we just saw periodic table which has rows, and rows are called the periods and the columns are called the groups. Now a little more. Usually the non-metals are all situated at the right hand side of the periodic table except hydrogen. Hydrogen is given on the left hand corner, but hydrogen is a non-metal. So the non-metals are given the dark blue, what we see in the slide on the right side. Whereas in that periodic table, if you look at the right hand side, almost the pink color elements, those are the non-metals. And then we have the metalloids, which are kind of border the stair step line with the exception of aluminum, polonium and astatine. Again, if you look at the slide here, you can see a bold line like going like a stair step, right? And in here, maybe if you look at here, this would be clear to you. So this area is all the non-metals, this corner. Then we have this stair pattern here. Can you see a color difference? The light green color. This is called the metalloids. Okay, this green line going right here. And rest all of them, all you see in this area with this blue color, they are all metals. So this is a main classification of periodic table. That is, these are all the non-metals, and the stairs pattern here, boron, silicon, germanium, what is AS? I forgot. So these guys, they are called the metalloids, and then here, everything what you see here is, including these, they are the metals. That is another classification of periodic table. And so again, metals are on the left side of the periodic table, as I said. So metals, metalloids and non-metals, that is one type of classification. As we go further, we will learn more about periodic table, as I mentioned. So right now, let's just remember this much about the periodic table. Elements are arranged in the order of their atomic number. We have periods and groups. The A-lettered groups are called the main groups or main group elements, and we will be focusing on them most of the time. And metals are found on the left side of the periodic table, non-metals on the right side, and metalloids in between, a stepwise pattern. Okay, let's just remember that much. Now we are going to look into chemical formulas. How do we write formulas, or how do we name things? That's what we are going to look at now. So when we write chemical formulas, we see a small number written as a subscript. And what are those subscripts? So the subscript to the right of a symbol of an element tells the number of atoms of that element in one molecule of the compound. So here is an example. Several molecules are given here. The first one is hydrogen. Hydrogen gas. If you take a molecule, it's 2 atoms of hydrogen joined together. So we will write H2. 2 is given as a subscript on the right side. Similarly for oxygen, O2. If you take water, we know that it's 2 hydrogens and 1 oxygen. So it is H2O. When an element is present only as 1 atom, we usually don't write it. So when you don't see a number on the right side as a subscript, that means there is only 1 atom of that element. Okay? So in water, H2O means there is only 1 oxygen. So we don't write the 1 after the oxygen. but hydrogen is 2, so we will write H2. Now, if you take H2O2, hydrogen peroxide, that is 2 hydrogens and 2 oxygens. Do not assume that they are closely related, the H2O2. Those are 2 entirely different chemical compounds, hydrogen peroxide and water. Then we can take carbon monoxide and carbon dioxide. As we see the formulas, CO for carbon monoxide. How many carbon and how many oxygens? 1 each. Carbon dioxide, CO2. How many carbon and how many oxygens? 1 carbon and 2 oxygen. Similarly, organic compounds, methane, first one natural gas, CH4, 1 carbon and 4 hydrogens, and another compound, ethylene, C2H4, 2 carbons and 4 hydrogens. Don't worry right now. Don't think that, oh, this is too much. How am I going to remember all these things? We are going to learn the systematic way of naming things. Right now, just see that subscript which is given at the right side specify the number of atoms of each element in one molecule of the compound. Now, here are 7 elements that will occur naturally as diatomic molecules. As the name suggests, diatomic means a molecule containing 2 atoms. So these 7 of them. So hydrogen, as we have just seen, so diatomic means when we just say hydrogen gas, we won't just write H, but we will write H2. When we say oxygen or nitrogen, once again, not just N, but N2. Similarly, O2, fluorine, F2, chlorine, Cl2, bromine, Br2, iodine, I2. So these 7 elements occur naturally as diatomic molecules in nature. So we write them all as diatomic molecules. Now, in the formulas also, there are 2 different types of formulas. One is called empirical formula and the other one is called molecular formula. What is the difference? Molecular formulas gives you the exact number of atoms in a particular, exact number of atoms of each element in a particular compound. Whereas empirical formula gives only the lowest whole number ratio of each element in a compound. Let me explain to you what do I mean by that. Here is an organic compound which we have just seen, C2H4, right? Ethylene, we just see that. Here is another organic compound, C3H6, hexene. These are 2 entirely different organic compounds. Okay? So what I have written down there is their molecular formulas. Ethylene, C2H4, it tells you exactly there are 2 carbons and 4 hydrogens in it, ethylene. And C3H6 is hexene and it says exactly 3 carbons and 6 hydrogens in one molecule of hexene. That's what it says. So these are the molecular formulas. Now, if I were to write their empirical formulas, what do I write? Remember, empirical formula is the lowest whole number ratio between atoms of each element. Yes. So if you look at the ratio between the carbon and hydrogen in ethylene, 2 to 4, is that the lowest possible ratio? 2 to 4 can be further reduced to 1 to 2, right? So you can write CH2. Remember, when we don't write anything, that means it is 1, right? So CH2, you can write like that for ethylene. The empirical formula for ethylene will be CH2. How about hexene? It will CH3. This is 3 to 6. So if you reduce that to the lowest possible ratio, what would you get? Once again, 1 to 2. 3 is a common factor. Yes.
Is this
No.
Would you put 2 and yeah, that's what
No. The molecular formulas gives you the names. The names comes from the molecular formula. Okay? Exactly how many are there. The empirical formulas just gives you the whole number ratio. Why we need the empirical formula is most of the times when a chemist discovers something, discover a particular chemical compound, the information they can first obtain is an empirical formula. That is what ratio each element is in there, before they isolate a single molecule and figure out how many of each of them are there. That is why empirical formulas comes into the picture. Most of the time we will be working with molecular formulas, and the names also comes from the molecular formulas. So here I'm just illustrating that two compounds can have the same empirical formula. That only means they have the same ratio of elements. That's all. Okay? But the actual number of atoms of each element could be different in two different compounds. So here also, if you look at the ratio 3 to 6, 3 is a common factor. So if you reduce this to the lowest term, you will again get 1 to 2, right? Or you can again write CH2. So note that both of these two different compounds can have the same empirical formula. As I said, empirical formula only tells you what is the ratio of elements in that. That's all. It doesn't tell you anything else. Whereas molecular formula gives you the exact number of atoms of each element in that particular compound. And when that changes, you are actually changing a compound.
Can you, for the molecular formula, can you keep it as an empirical but put the 2 out in front, or do you want the numbers?
No, when you put the 2 out in front, it is not the same as the molecular formula. It's going to be different. That's going to be the coefficient, which we will learn in chapter 3. Okay? So right now let's just focus on what we write as the subscript on the right side. Now, so we just saw empirical formula and molecular formula. Now another types of formulas, we can look at the structural formulas and perspective drawings. So structural formulas will show you the order in which the atoms are bonded. As the name suggests, structural formula, how actually the structure of the molecule is going to be, how it is connected, the connectivity. That's what the structural formula will tell you. And perspective drawings, that is the, let's just take this molecule. CH4, molecular formula is CH4. Means it is telling you exactly how many carbon atoms are there, how many hydrogen atoms are there. Okay? CH4. Now, there is no empirical formula there because that is the lowest possible ratio. It's 1 to 4. You cannot reduce it any further. So, molecular formula and empirical formula for this particular molecule is the same. Then comes structural formula. So, this is showing you the connectivity. You might be wondering, CH4, is it 1 carbon and then 4 hydrogens in a chain? It is not. So if you look at the structural formula, this actually gives you the arrangement of atoms in that element. So we can see that carbon is in the middle and 4 hydrogens are around the carbon. So that tells you the structure. Now the structural formula is only a 2-dimensional picture, right? It doesn't give you the actual angles between the element arrangement. Or another way of saying that is, if you look at this picture, it looks like this angle is 90 degrees, right? Based on the geometry, it looks like a right angle. It's like 90 degrees. But actually, if you look at the 3-dimensional molecule, the angle is much more than 90. It comes to 109.5. So, the perspective drawing is kind of trying to give that idea, okay? It's not just 90-degree angle, it is a different arrangement, or in 3-dimension it will look different. So it's trying to put, see, this carbon with these 2 hydrogens, that is on the plane of the paper, you see, and then look at these 2 hydrogens, how they are drawn. The solid line, what you see is, you have to imagine that one as coming out of the plane of the paper, coming towards you, okay? And the one with the dash line is on the back of the paper. So if you just look at this whiteboard, then this is the plane of the paper, and this guy should be jumping out of this board, and this hydrogen with that dotted lines should be going to the other side of this board. Okay, so that will be the 3 dimensions. So the perspective drawing is kind of showing you the 3-dimensional arrangement. Now further, if you really want to see the molecule, you can make a ball and stick model. You will be having a lab where you will play with different molecules models. We will be making a lot of models of the molecules. So ball and stick, each ball represent an atom, and sticks we use them to show the connectivity, how they are connected. Okay, so that is the ball and stick model. But the space filling model is kind of giving you an idea of actually the molecular size, how it's related to each element, how the size is going to be. So that's the last one, the space filling model. So these are all different types of representing a molecule, which you will be seeing further. Now the next topic we will look at is ions. So far we were focusing only on atoms. Now we are going to look at what are ions. So when a neutral atom lose or gain electrons, it forms an ion. So before we go to the ions, let's remember one more thing. We said in last class, a neutral atom has equal number of protons and electrons, right? Then only it can be neutral. The positive charges has to be exactly cancelled by the negative charges. Now, here is an atom which lose some electrons. What does that mean? Now, do we have a charge balance? We don't, right? Because it lost some electrons means some negative charges has been taken away. So you have a extra positive charge in your overall existence. Similarly, another atom which gained some electrons. Again, do we have charge balance? No. Gaining electron means what? You have extra negative charge now, because remember, electrons, each electron is one negative charge, right? So if you are gaining a few extra electrons, you are gaining a few negative charges. So now you have overall negative charge. So when an atom loses electrons or gain electrons, there is a charge imbalance, and the atom could be either positive in nature or negative in nature. And that time we won't call it just an atom, we call it an ion. Okay? So there can be two different types of ions. One is called cations, and cations are positively charged ions. And how do we get cations? Cations are, what does it say? Cations are positive and are formed by elements on the left side of the periodic table. Okay, so left side of the periodic table we have metals. That's what we said. Left side of the periodic table mostly contain metals. And metals form positively charged ions. What does that mean? They lose electron or gain electron? They lose electrons, right? If somebody lost an electron, then one negative charge is taken away, so you have a proton's charge which is not cancelled away. So overall you have positive charge. So similarly, anions, the other way. Anions are negatively charged ions. And how can you get negative charge? By gaining electrons or having extra electrons. And usually the non-metals gain electrons and becomes negative, or they form negatively charged ions. So as we said, we are going to focus only on the main group. So the first group and second group, they are mostly non-metals, and this is why hydrogen, even though, they are metals, and even though hydrogen is a non-metal, why we put it above group 1 is usually hydrogen forms a positive ion, H+. Okay, and then if you come to this side, in group 3 we will be focusing only on aluminum, because rest of the group 3 are either transition metals or metalloid. which have different properties, so we don't worry about them. Now group 4 is kind of special. We will learn why later. So that is why nothing is given in group 4A. And then 5A, mostly we will see nitrogen, sometimes phosphorus also. Group 6, we will see oxygen and sulfur very often, and we will see selenium and tellurium also. And group 7, the halogens, we will see fluorine, chlorine, bromine, iodine very often. Now hydrogen is special. It can form positive and negative ion. Most of the times it's positive, but it can form negative also, an H minus. So that time we will say the hydrogen is kind of like the halogens. And then we have group 8A, noble gases, which do not form ions. Okay? Now we will see why these charges are like this. There are reasons behind it. Right now let's just see cations and anions. Cations are positively charged ions. Anions are negatively charged ions. Positively charged ions means that atom has lost some electrons. Negatively charged ion means that particular atom has gained some electrons. And based on how many electrons it lost or how many electrons it gained, the charge is plus, 2 plus, 3 plus, so on, or 3 minus, 2 minus, and just 1 minus, and so on. So once again, why ions form? Noble gases, the group 8A elements we see on the rightmost side of the periodic table. The noble gases have a very stable arrangement of electrons. We will learn again what is electronic arrangement and their details later. I know I keep saying that, right? We will learn a lot of things later. Yeah, this is only the, kind of a gist of what you are going to learn later in the semester. We will learn all these things in very detail. Don't worry. This is just kind of an overview. So noble gas elements have a very stable arrangement of electrons, and they are chemically non-reactive and form very few compounds. Every other element in the periodic table, their goal is to be like the noble gas. Okay? So noble gases, that name itself, they have a particular nobility. They are kind of special. They are just above everyone. So just like, us, if we find someone up there, we all want to be like that successful person, right? That is, human nature. Just like that, all these other elements, they want to be like the noble gases. So what they do is, they will try to have the same kind of electronic arrangement as the noble gas. In order to reach there, they will either lose electrons or gain electrons. Okay? So this gaining or losing electron comes from that desire to become like a noble gas. Now, having said that, before we go to the ionic compound, let's look at this table one more time. Having said that, this might make sense now. Let's look at group 1 elements here. Okay, lithium, sodium, potassium, rubidium onwards. Here, this will be easier because it has the atomic number. Let's say sodium right here. Everyone see sodium? Number 11, atomic number. So it has 11 protons and 11 electrons. It is neutral. Now sodium's goal is to become like a noble gas or become like the nearby noble gas. So sodium has two options. Either sodium can look up to this guy here, argon, which is so far away, like sodium atomic number here 11, and to be like argon number 18, how many electrons it has to gain? Now it has only 11 electrons. To become like argon, it has to gain how many electrons? Like 7 of them, right? Now let's see. Sodium has another option. Just before sodium, number 10, neon. which is another noble gas. How many electrons neon has? 10. Now, if you are 11, which is easier, to go up to 18 or to go to 10? Going to 10 is much more easier than going all the way to 18, right? So what sodium does is easily just lose one electron. When sodium loses one electron, now how many electrons sodium has? 10 electrons, like neon. So he is happy now. He is feeling that pseudo nobility. Oh, I am like neon now. I have the same number of electrons. But what happens to the charge? 11 protons, 11 electrons, 1 electron gone, 1 negative charge gone. So what will be the overall charge now? 1 positive, because from the 11 protons, there are 10 electrons to cancel 10 positive charges, but the 11th proton's charge is not cancelled now, because that 11th electron is gone. So the overall charge will be just 1 positive. Just like that, all of them, the group 1 elements, everyone's the same case, right? Potassium number 19, instead of going all the way to 36, it will just lose 1 electron and become like argon, who is 18. So if you understand that, all of these guys, they will always form 1 plus ion, because it's easy for them to lose an electron and become like just the previous noble gas than gaining all these electrons to become like the noble gas after them. So that is group 1 elements. So you can remember this, group 1 elements, lithium up to francium, they will always form 1 plus ion. Okay? Similarly for group 2, this also can be explained using the same philosophy. Let's take the example of calcium, number 20. Calcium wants to be like a noble gas, which is easy, going all the way to 36 or from 20 going to 18, which is easy. Going to 18 is easy. So from 20, if you have to go to 18, how many electrons it has to lose? 2 electrons. Now, 2 electrons is gone, means 2 negative charge is gone. So how many protons are there whose charges are not balanced? 2. Therefore, the charge of calcium is 2 plus. Similarly, all of them, it's easy for them to lose 2 electrons and becomes 2 plus ion rather than gaining so many electrons to become one of the noble gases. That is the history behind 1 plus and 2 plus ions for group 1 and group 2. Now, if you come to group 3, again we will focus only on aluminum. Same principle. For aluminum, it's 13. Instead of going to 18, it will just lose 3 electrons and become like neon. So aluminum is always 3 plus. Now let's come to group 4. Say for example, carbon. Okay, number 6. Group 4A, this guy is right in the middle. If you look at his position, either he can jump these 3 places and become like neon, or he can go backward 3 places and become like helium. So the distance is right exactly the same, going this way or this way, exactly the same, right? That is why we are not seeing in the periodic table of, right there, 4 is left vacant, because based on other factors, again which we will learn later, this could be either positive or negative. If it is going this way, then it becomes negative. If it is going this way, it becomes positive. So we will not focus on group 4 right now. We will just leave it blank right now. Now comes to group 5, nitrogen. First one in group 5A. Okay? Nitrogen is right here. Number 7. Let's think again. Nitrogen wants to be like a noble gas. Going this way is easy, or going all the way back to helium is easy? Going to neon is easy. Nitrogen is 7. Going to 10 is easier than going all the way back to 5. Right? Now, from 7, nitrogen has 7 electrons and 7 protons now. It wants to have 10 electrons. How many electrons it needs? 3. 3 more electrons. It has 7 now. In order to be 10 electrons, it needs 3 more. So it gains 3 electrons. Gaining 3 electrons means how many negative charges it has gained? 3 negative. Therefore, nitrogen is always 3 negative because it will gain 3 electrons. Phosphorus, most of the time it does exactly what nitrogen does. It will gain 3 electrons. But there are cases where phosphorus can have different charge. That is why it is not given there. Whatever is given in that picture, those are fixed. Okay? Those ions, they will always be of that charge. So oxygen, again now we can figure this out. Oxygen is number 8. Gaining 2 electrons and becoming 10 is much more easier than losing like 6 and going to 2. Right? So oxygen is always 2 negative. It gains 2 electrons and becomes like neon. Of course, fluorine stays next to neon, so it just wants 1 more electron and becomes like neon. It doesn't want to lose so many and go back to 2. So it's the same case with all of them in group 7A. Fluorine, chlorine, bromine, iodine. Everyone, they are all close to the noble gases. All they need is just 1 more electron. So they will always gain that 1 electron and becomes 1 minus ions. Now it makes sense why we see these numbers. It's because of their positions in the periodic table, and the basic concept is they all want to be like the noble gases. They cannot be like the noble gases, exactly like the noble gases, but at least they try to achieve their electronic configuration so that, at one level they feel like, okay, we are just like them. Okay? So by looking at the position, we can predict the charges of these ions. Questions so far? So now it makes sense why these ions form, because they want to be like the noble gases. So now we are going to look at ionic compounds. Just stretching, right? Yes. No questions? Okay. So ionic compounds such as NaCl, sodium chloride, are generally formed between metals and non-metals. So we just talked about ions. So mostly the metals will form positive ions and non-metals will form negative ions. Now when we learned about charges in last class, we said that opposite charges will attract each other, same charges will repel each other. So if you have positive charge and negative charge at one place, they are bound to be together, right? They are going to attract each other and they are bound to be together. So ionic compounds are formed in such way, that is, you have positively charged metal ions and negatively charged non-metal ions, so those opposite charges will attract each other and you will have an ionic compound. Let's look into the detail of, let's say, how sodium chloride is formed. Normal neutral sodium atom, as we said, atomic number is 11, so it has 11 protons in the nucleus and 11 electrons in the, outside the nucleus, right? That is the normal sodium atom. Now sodium wants to be like neon, so it will lose 1 electron. Now it still has the 11 positive charges in the nucleus, but there are only 10 electrons outside, and we will call it an Na plus ion. So now let's take chlorine. Normal chlorine, 17 is the atomic number, so 17 protons and 17 electrons. Chlorine will gain an electron and it will now have 18 electrons and 17 protons. We call it Cl minus ion. So here we see sodium lose an electron. So when somebody loses an electron, where does that go? Is there a pool somewhere out in the space where all those electrons can go and stay? No. So somebody lose an electron means simultaneously someone else absorb it or someone else gain it. Okay? So here when sodium loses an electron, it's not going anywhere to, for a vacation. Actually, so chlorine is right there waiting for that electron. Or similarly, when we say chlorine gains an electron, where does it gain from? There is no pool where somebody can go and, okay, I want 2 electrons, come up. So there are no electron pool waiting there. So this gaining and losing is relative. Okay? So when sodium loses 1 electron, chlorine gains that. And now you have Na plus and Cl minus. Once you get Na plus and Cl minus, note that it's positive and negative charge species. They are going to attract each other. They come together and make sodium chloride, NaCl. So once again, the positive charge and negative charge are cancelled each other. Therefore, when we write the sodium chloride, there is no charge overall. The compound is electrically neutral. Okay? That is how an ionic compound will form. Now, another type of compounds, we can call them molecular compounds. Molecular compounds are composed of molecules and almost contain only non-metals. So when compounds form only between non-metals, they are called molecular compounds. Now, molecular compounds do not follow this ion formation and electric charge attraction and all that stuff. Okay? In molecular compounds, there is no such specific rules of only ions of a certain type will come together. There is a ratio, nothing like that. Molecular compounds are formed with various non-metals. Here are some examples. What we see here, they are all compounds formed with non-metals only, like water, hydrogen and oxygen, both are non-metals, and hydrogen peroxide, again hydrogen and oxygen, both are non-metals. Carbon monoxide and dioxide, both non-metals, methane, ethylene. So these are all examples of molecular compounds. So 2 different types of compounds, ionic compounds and molecular compounds. Molecular compounds formed between non-metals, ionic compounds formed between a metal and a non-metal or oppositely charged ions. Now, if you look into human life, if you see our human body is made up of a lot of these elements. We have a lot of these elements in our body, and this is just, 6 most abundant and essential elements: carbon, nitrogen, oxygen, phosphorus, sulfur and hydrogen. Our body mostly is made of carbohydrates. Carbohydrates, as the name suggests, it has carbon, hydrogen and oxygen. And then a lot of our proteins and lipids and amino acids, everything, they are all contain carbon, hydrogen, oxygen, definitely, and then either phosphorus or sulfur or nitrogen in various quantities. Okay, mostly our body is made up of, as we know, proteins and muscles and all that stuff. That is all made of those 6 essential elements. Then the 5 next most abundant and essential elements, like sodium, magnesium, calcium, potassium, chlorine, which we call our electrolytes, right? Those are the next most abundant and essential elements. And then the rest of these other green ones, they are needed only in trace quantities. So if you look into the complete multivitamin label, you might see some of those, selenium, manganese, all that stuff written there. So that is all what you need in trace quantities. So nothing to worry about this slide. It's just for, kind of a general knowledge thing. Okay, so we talked about ions. Now we are going to learn how do we write formulas. So even though compounds, ionic compounds formed from oppositely charged ions, electrically they are always neutral, or the ions come together in such a way that the electrical neutrality is maintained. And how do we write the formulas? Let's take the example of magnesium ion and nitride ion. Magnesium, Mg in group 2A, Therefore, the charge is going to be 2 plus. Remember, as I said, group 1A elements, always the charge is 1 plus. Group 2A elements, the charge is going to be always 2 plus. So magnesium is 2 plus and nitrogen in group 5A, and we said to become like a noble gas in group 8, it will gain 3 electrons, so nitrogen is going to be 3 minus. So when they come together, they form a compound called magnesium nitride. And how do we figure out how many of magnesium ions and how many nitride ions should be joining together? The key point is, once they form a compound, they should be electrically neutral. How can we make sure? All you need to do is this, as it shows in this picture. Put the charge of the positive ion as the subscript of the negative ion, and the charge of the negative ion becomes the subscript of the positive ion. So you get the formula Mg3N2. Okay, this is an easy way of remembering. You have to understand the concept in case if you don't remember this. So once again, let's take Mg2 plus and N3 minus. If you take one Mg2 plus and one N3 minus and join them together, and if you just write Mgn, is that electrically neutral? It is not. Here is 2 plus and 3 minus, so they are not cancelling each other, right? In order to be electrically neutral, total number of positive charge should be exactly the same as total number of negative charge, right? Okay, so a 1-1 doesn't work. So where do we have a charge imbalance? This is 2 plus and this is 3 minus. So if you write this way, you have overall 1 extra negative charge. So let's say we will add another Mg. So let's say we have now Mg2n. Is that electrically neutral? Mg2 means now 2 times 2 plus, this is total giving you 4 positive charge. There is only one nitrogen which is giving you 3 minus. So 4 plus and 3 minus. Still we are not neutral. Right? Okay, you are going to add one more nitrogen. So now we have Mg2N2. Are they neutral? Mg2 will give you 4 positive charge. N2 will give you 6 negative charge because 1N is 3 minus. So 2 will give you 6 negative charge. Still not good. Okay. What if we add one more Mg? Mg3N2. Now look at the charges. 3 magnesium will give you 6 positive charge. 2 nitrogens will give you 6 negative charge. Now it becomes electrically neutral. Right? That is where we get the correct formula, Mg3N2. So instead of going through this tedious process of checking one by one until, and adding one by one until you get them electrically neutral, you can remember this easy step, that is switching their numbers and writing it as the subscripts. Okay? So this 2 plus, Mg2 plus, we will forget about this positive and negative sign, but this 2 will go for the subscript as for the nitrogen. So that is how you get the N2, and N is 3 minus, forget about the negative charge or negative sign, this 3 will go as the subscript for Mg, so you get Mg3. They will always work. Say for example NaCl, Na plus ion and Cl minus ion, 1 plus and 1 minus, right? So if you just switch, you will just get NaCl, 1, 1, they are good. How about calcium chloride? If you want to write calcium chloride, calcium is in group 2, so what will be the charge? 2 plus. Chloride is in group 7, so the charge will always be negative. Now let's switch their places. 2 will go as the subscript for chlorine and 1 will go as the subscript for calcium. So 1 will go as the subscript for calcium, so Ca, and Cl2, and that is the formula of calcium chloride. Now you look at the charges. 1 Ca is 2 positive charge. 1 chlorine is 1 negative. In order to balance the 2 positive charge, how many chlorines you need? 2. So CaCl2 is electrically neutral. It will always work if you do this carefully like this.
What if they're 2 and 2?
2 and 2. Then you don't have to write anything because again the lowest ratio is like, remember as I said, when it is just 1 we don't write anything. Right? So say for example, we want to write calcium oxide. So calcium is 2 plus, oxide is 2 minus. If you switch their places, what you are getting is Ca2O2. Right? When we get something like this, we will further reduce it to its lowest terms. So we will write the formula as CaO. So calcium oxide is CaO. Make sense? Because as I said, the basic concept comes from total positive charge should be balanced by the total negative charge. So for calcium oxide, 1 calcium 2 plus, 1 oxygen 2 minus, so they are electrically balanced. So you don't need any further there. Do practice exercise 2.10. I guess that will be for writing formulas. Let's do that. Where is 2.10? If anyone find it, let me know the page. 58? Okay. Okay, 2.10. Using ionic charge to write empirical formulas for ionic compounds. Let's look at the sample exercise first. And then we will do the practice one. So, write the empirical formula of the compound formed by Al3 plus ions and Cl minus ions, and then Al3 plus ions and O2 minus ions, and then Mg2 plus ions and NO3 minus ions. Okay. So, the first one, let's look at the solution also. Al3 plus and Cl minus. So, aluminum is 3 plus, Cl is 1 minus. In order to be electrically neutral, you need 3 positive charge and 3 negative charge, right? So for each aluminum, how many chlorines you need? 3. So you'll get the formula AlCl3. It will work if you switch just the numbers also. Cl 1 minus, so put 1 for aluminum, aluminum 3 plus, so put 3 for chlorine. Again you will get AlCl3. So whichever way your thought work, you will get the right answer. Right? Now Al3 plus and O2 minus. Switch the places and see. Are you for the chemistry?
No, math.
Math is not started yet. That starts at 3:30.
Oh, yeah, gotcha.
Okay.
It's early.
Yeah. So,
Even last time.
I know. We should ask us, I don't know, he was looking at the phone or something, which should be from the satellite. So it should be correct. Anyway, so Al3 plus and O2 minus. Once again, if you switch the places, 3 will go as a subscript for O and 2 will go for aluminum. So you should get Al2O3. Now if you look at the charges also, Al2 means 2 aluminums, total positive charge is 6 plus, because each aluminum is 3 plus, so 2 aluminums will give you 6 plus, and oxygens, each oxygen is 2 minus, so 3 oxygens will give you 6 minus. So 6 plus, 6 minus, electrically neutral. Last one, Mg2 plus and NO3 minus ions. I know you haven't seen that NO3 minus ions so far. We will see that in probably next slide. Right now let's just focus only on that charges. So Mg is 2 positive charge, each NO3 is only 1 minus charge. So to be electrically neutral, how many NO3s you need? 2 NO3s, right? So you will switch their places. Now here, Mg2 plus and NO3 minus. So if you switch the places, you should need 1 Mg and NO3s, how many we need? 2. Here is a special case. Where do I write that 2? Because this species, it already has a 3 in here. So can I go and write a 2 next to it? There is a confusion. That could be read as 32, which is not correct. Can I put a 2 here in between? I cannot. So when you have a species like this, which already, this is called a polyatomic ion. As the name suggests, more than, polyatomic means more than one atom. So a polyatomic species, when you have a polyatomic species, what we do is, we will put that species in a set of parentheses and then write the number outside. So we will write Mg NO3, we will put the NO3 in parentheses, and how many NO3s we need? 2, so write that 2 outside. So now there is no confusion. This means 1 Mg and 2 NO3s. Charge is again balanced. 1 Mg is 2 plus, 1 NO3 is 1 minus, so 2 NO3 is 2 minus. Okay? Now let's do the practice problem. So write the empirical formula for the compound formed by Na plus and PO4 3 minus. So Na plus and PO4 3 minus. So again another polyatomic group, its charge is 3 minus. So this 3 will go for Na. So we will get what? Na3, right? The 3 goes for Na, right? So Na3 and Na plus means the number here is 1. The 1 will go here. So we have PO4 and there is only one PO4. So do I have to put it in parentheses and write 1 outside? I don't have to. Remember, when it is only 1, we just write the symbol. We don't specifically say there is only 1. When you see the symbol, that means there is at least 1, right? So the formula will become Na3PO4. The second case is zinc 2 plus and SO4 2 minus. So, zinc 2 plus and SO4, another polyatomic ion, 2 minus. Look at the charges. How many we need each of them to be balanced? Just 1, 1, right? There is 2 plus and 2 minus. So if you take 1, 1, it's good. So how do we write the formula? Cn SO4. Okay? Remember, as I said, you can write it in the lowest possible ratio. So instead of writing Cn2 SO4 2, you can just write Cn SO4. 1, 1 will give you the charge balance. Now the last case, Fe3 plus and CO3 2 minus. I am surprised why we are seeing all these polyatomic ions and the slides haven't talked about that. Oh, okay. Next slide is the ion names. Okay. So Fe3 plus and CO3 2 minus. Okay, let's switch the places. So Fe will have what? 2, because this 2 will become, this 2 will come here, and CO3 should get this 3. So that means we have to put CO3 in parentheses and write the 3 outside. So Fe2 and CO3 in parentheses and 3 outside. Again, if you look at the charges, this way it is balanced. Each Fe is 3 positive. So 2Fe will give you a total of 6 positive charge. Each CO3 is 2 negative. 3 CO3s will give you 3 times 2 negative, 6 minus charge. So the charge is balanced. Let's stop right here today. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, goodness. Somebody is not here. Who is that? 15. So that means I need to take the attendance. Come on, guys. I don't want to